So good afternoon. We will start our discussion. I'm not still in very good condition, so but the time is running out for taking the classes because I think next week is the last week of academic calendar before the semester exams. So that's why I thought that I would try to take this class gingerly as and see how far we can progress. Okay. So our CFD course. I hope you can hear me. I will try to speak a little less loudly, but generally I forget, so I will start speaking loudly only. So the CFD course is actually was about to finish. So it would have gotten finished or completed by this week itself if I had not contracted COVID. So it will take just one or two more classes to finish the CFD part. The main issue is with the power plant engineering course where a lot of material is left. So that I would like to have a discussion after this class today on how to proceed about that, because the material is very important also from both perspective of say competitive exams like GATE and other exams, and in general also because we have not yet discussed about turbines, and turbines are the one of the most important part of power plant engineering. So that has to be covered in depth. So we do not want to compromise there the quality of the material, or we do not want to reduce any material. Okay, if it takes more classes, we will take more classes and finish it properly. So anyway, let us come back to CFD. And so before today's class we were basically discussing about convection diffusion problems, right? And what we had noted was that in convection diffusion problems, so if we ignore the source term and the transient term, which are very easy to tackle, we already know how to tackle them. We are left with two terms. What are those two terms? The two terms were the advective term ddx of rho u phi and the diffusive term ddx of gamma d phi dx. Okay, so we had devised two schemes for solving this or for discretizing this. One we had called as central difference scheme, and another one we had called as upwind scheme. And we saw the pros and cons of each of those schemes. Okay, what are the advantages and disadvantages when they are valid? Okay, at what ranges of Peclet number they are valid. We saw that for very small convection, means if the Peclet number is small, then the central difference scheme is valid, and when the Peclet number is very large, means when the convection or advection is very large and diffusion is small, the upwind scheme is valid. Okay. Then our target was to actually see what is the variation of the simple problem, simple 1D problem. For this case, actually how phi varies between two grid points. Okay, instead of just trying to fit random curves like straight line or step line or something like that, quadratic line, we want to actually see what is the variation. And we solve this equation analytically in non-dimensional form. We have already discussed this. I am not going to details. I will upload all this video in YouTube in 1 or 2 days once I feel little better. So after solving, we found that the variation is exponential. Okay, and this was the variation that we had obtained. So for Peclet number much greater than 0, means very high advection or very high flow along the positive direction, the value of phi varies in this manner. So the value of phi in the almost the entire region in between two grid points is equal to the value of phi in the upstream side of the upstream grid point, which is understandable because the flow is coming from this direction, so this value should have a strong influence. Okay. On the other end, if the Peclet number is strongly negative, means the flow is coming from the right to the left with a very high velocity, this side, now this becomes the upstream side, so this point value actually dominates the entire value of phi for the almost the entire region, only except the last region. Okay, and if there is not much flow, if Peclet number is 0, so there is no flow at all, then the variation is diffusion dominated, in which case the phi actually varies linearly. Diffusion dominated phi will be linear, will show linear variation. So this blue line shows that kind of variation, that linear variation. This we have seen. Okay, so we can assume that this we can assume that we have this type of variation even in between the grid points. Okay, although this has been derived keeping in mind 1D convection diffusion equation without source term and without unsteady term, but for even complex problem also we can assume that at least somewhat similar behavior will be there, and based on that we can fix our profile assumption. So this is what we had discussed in the next class, means we have already discussed this also. Like if there we have two grid points, adjacent grid points P and E, the variation between P and E can be governed by this type of exponential variation. If P is much, Peclet number, this P is different, Peclet number, okay, this P is different. If Peclet number is greater than 0, we have this type of variation. If the Peclet number is less than 0, we have this type of variation, and for Peclet number 0, we have a linear variation. Between phi is equal to phi P at the grid point P and phi is equal to phi E at the grid point E. Okay. So based on this, we have derived a scheme, okay, which was known as the exponential scheme because it is developed based on this exponential solution. Okay. And this also we have discussed. If you don't remember, you can go back to the notes. Just based on our equations, we have derived a scheme, and finally this scheme will also give, so all these schemes, remember, will give the same discretized equation, or the form of the equation will remain same. AP phi P is equal to AE phi plus AW phi W, okay, plus if source terms are there, so B. Okay. The only thing that is varying is what is AP, what is AE, and what is AW. So in this case, AE and AW are obtained based on the exponential variation. Okay. So this is given by this form, Fe by e to the power Pe minus 1, and AW is given by Fw e to the power Pw by e to the power Pw minus 1. This can be easily derived. We have already derived this in the previous class. You can again go through it if you don't remember. It's not a difficult task. And AP is equal to AE plus AW plus Fe minus Fw, and by continuity equation, because Fe is equal to Fw, ultimately AP is equal to AE plus AW. Okay, so once you know what is AE and AW, you can always find AP. So up to this point we had discussed, and we had discussed that this scheme is known as exponential scheme. The main advantage of this scheme is that however coarse grid structure you take, means if you take very few number of grid points, okay, in a domain, still you will get the exactly correct solution for a 1D steady state problem, okay, because you are defining the scheme itself based on the correct solution. Your solution will be correct in the numerical problem also. However, for 2D or 3D problem, or for unsteady cases or with source term, the solution will not be correct but will be very accurate. Okay, the solution will be very accurate, although it will not be exactly correct 100%. It will be very accurate as compared to the other schemes. Now the main drawback of this, if there was no drawback, we would have used this scheme always because it is very accurate. However, the calculation of this exponential terms are very computationally intensive. Okay, each exponential actually takes a lot of computational effort to calculate. So e to the power p, this you have to calculate using a sum of a infinite series. Okay, in numerical form. So directly you cannot calculate what is e to the power p. If you type in MATLAB or in your calculator, it actually calculates based on sum of series. So you have to calculate each of the terms, multiply, like there are multiplications for each of the terms of the series, and then there are additions. So it takes a lot of effort to calculate single exponential. So this scheme is very computationally intensive. If you have large number of grid points, it is not possible to use this scheme. Okay. So that is the only drawback and the major drawback. So it cannot be used because of this major drawback. Okay. So what do we need? We need some scheme which can mimic the behavior of the exponential scheme. Okay. So which will mimic this behavior, that the variation is somewhat similar to this. However, it should not have any exponentials in its calculation. Okay, it can have terms like quadratic term or linear term or something like that. Okay, but no exponential terms. Okay, some power also is fine, but no exponential terms. So instead of using exponential, if we can use some other type of terms but mimic the behavior or replicate the behavior, then that is a scheme that we want, because then it will be easy to compute as well as its behavior will be similar to exponential scheme. So it will be very accurate. Okay. So this can be devised using piecewise linear functions. Okay, or piecewise functions, need not be linear also. Like we can break down the profile into 3-4 different parts, and each of the part can have a different equation. So by using 3 or 4 equations, we can represent the entire variation in part by part. Okay, so this is what is called as piecewise function. So if the parts are linear, then it is a piecewise linear function. If the parts are non-linear, it need not be piecewise linear. Okay, so this is our target, and based on this, we will briefly see the two other schemes, which are the last two schemes that we are going to study, and which are much more accurate and are generally used nowadays in many applications. Okay, one of the schemes is very popular, which is known as power law scheme, and is used for many applications. Okay, because its accuracy is almost similar to, there is not at all, means you will not be able to find much variation between this scheme and the exponential scheme. However, the calculation is much simpler. Okay, we will study before that another scheme which is known as hybrid scheme, and then we will study the power law scheme. So let us go to, so up to this we had discussed in the previous class. So I just wanted to bring continuity to our previous discussion. Any questions on the previous material? I guess no questions then. I guess I need to take frequent breaks. Okay, so this next scheme is known as hybrid scheme. Okay, let us try to understand this hybrid scheme. So to do this, we will keep the analytical, we will keep the exponential scheme open in the other tab. Okay, so if you see the exponential scheme, this is open in the right hand side. Okay, AP 5P is equal to AE 5 plus AW 5W. It will look small in your screen, but those who are using monitors or laptops should be able to see. So AE is equal to FE by e to the power P minus 1. Okay, this is AE. FE by e to the power P minus 1. Let us try to understand this behavior of AE. Okay. Why we will try to understand this behavior of AE? Because this gives us hint about the nature of the scheme. Means if AE is say very large, it means that phi E has a strong influence. If AE is 0, it means that phi does not have any influence. If AE is 1, it means that phi has some influence. Okay. So depending on the value of AE, if AE is negative or positive or whatever is the variation, it gives us an idea about what is the influence of phi E. Okay, and this AE variation, AE will vary depending on the Peclet number. Okay, so because AE is a function of Peclet number, as you can see from here. Okay, so we want to see the nature of AE, nature of variation of AE with Peclet number. So we will write this AE in a non-dimensional form. Okay, by dividing it by DE. DE, if you remember, if DE is the diffusive strength, gamma by delta x. Okay, gamma E by delta x. So by dividing by D, we can write this as Fe by D by e to the power P minus 1. So Fe by D, if you remember, is Peclet number P. Okay. So it becomes P by e to the power P minus 1. It's a non-dimensional number. So this A by D is known as non-dimensional coefficient of phi. Okay. So basically we are going to study the behavior of this non-dimensional coefficient of phi E. Okay. With various Peclet number Pe. Let us see how it varies. Okay, so if Peclet number tends to positive infinity. Okay, if Peclet number tends to positive infinity, what is the value of p by e to the power p minus 1? Okay. Both the numerator and denominator tends to infinity. Okay, if Peclet number tends to positive infinity, but what is the ratio? Let us try to see. So a by d is equal to limit Peclet number tends to infinity p by e to the power p minus 1. Okay. So if you don't remember, there is a rule called L'Hopital's rule. Okay, written as L Hospital's rule, pronounced as L'Hopital's rule. Okay. So this states that for this particular case, there are different variations of this L'Hopital's rule. For our particular case, limit x tends to infinity fx by gx, where fx and gx are two differentiable functions. Okay, limit x tends to infinity fx by gx is equal to limit x tends to infinity f dash x by g dash x. Okay, this is valid if g dash x is not equal to 0. Okay, this is one variation of L'Hopital's rule. You can read about this in any book or even in Wikipedia also you can read. Very famous actually. So we can convert the limit in terms of their derivatives, in terms of the derivatives of the numerator and denominator, because otherwise we are unable to find the limit for this, because we are getting infinity in both the numerator and denominator. Okay, so now we will use L'Hopital's rule here. Okay, so differentiate with respect to Peclet number. So p differentiation with respect to Peclet number is 1. Okay, and the denominator e to the power p minus 1 differentiation with respect to Peclet number is e to the power p. Okay, so limit Peclet number tends to infinity 1 by e to the power p. So as Peclet number tends to infinity, this term goes to the denominator goes to infinity, numerator is 1. So the entire term goes to 0. Okay, this is understandable. Even without a L'Hopital's rule, you can see the numerator increases only linearly with Peclet number. The denominator increases exponentially with Peclet number. So the denominator will be, although both goes to infinity, the denominator goes to very large infinity as compared to the numerator. Okay, all infinities are not equal. So anyway, this would have been equal to 0 at the limit that Peclet number tends to infinity, but we can mathematically prove that a by d is equal to 0 if Peclet number is positive infinity. Okay, let us keep this in mind. So a by d, non-dimensional a is equal to 0 for very large value of Peclet number, positive Peclet number. Okay, what does it mean? What does it mean physically? Let me open this. Okay, this is we have already discussed for the exponential case. Peclet number means Peclet number is very large. A tends to 0. What does it mean? A by d tends to 0 for very large Peclet number. In the discretized equation, what will be the influence of phi e, value at e, if the Peclet number is very large? Anyone is there? Aniket? Aniket, you are there? No response. Jagadish?
Yes, sir. Advective strength will be very dominant, sir.
Advective strength is dominant. What will be the influence of phi e if Peclet number is very large?
So the like immediate tries to phi capital, sir.
You could not understand your point. So we have two values, right? Phi is equal to phi p at one point and phi is equal to phi e at the other point. Okay. Now we are trying to find the variation between these two grid points. Okay. Now if we are saying that and based on this variation we are getting the discretized equation also. So if A is equal to 0, it means that, so what, how the equation looks like? The equation looks like this. AP5 is equal to AE5 plus AW 5W. If A is 0, so what is the influence of phi? It is 0, right? Means phi does not have any influence. So ultimately phi p is influenced by its upstream side W only, right? It is not influenced by the downstream side. Okay. So in the full discretized equation for the grid point P, the value at P is influenced only by its upstream side, means from the left hand side, from where the flow is coming. Okay. The downstream side does not have any influence. Why? Because the flow is coming with a very strong influence from the left to the right. Is it clear to everyone what I am trying to say?
Yes, sir.
Yes, sir. Yes, sir.
So now can you say what will be the value of AW if, when will AW be 0? At for what value of Peclet number AW will be 0? A is 0 when very large Peclet number is there, positive. So for what value of Peclet number AW will be 0?
Minus infinity.
Minus infinity, good, correct. Because at minus infinity flow is coming very strongly from the other direction, from the right to the left. So W should not have any influence on P. E will have the dominant influence on the grid point value P. Okay. So anyway, we are digressing, but that is the physical meaning. Okay. And that is what we have obtained also, that for very large Peclet number, A by D is 0. It means that the influence of, I will keep this open. Okay. The influence of phi is negligible for large Peclet number. Okay. Now let us see the value of A by D when Peclet number is very large negative number. So Peclet number tends to negative infinity. What do you expect? What will be the value? Means will there be any value of, will it be 0 or non-zero? If the Peclet number is very large negative, okay, what should be the value of A? Will it be 0 or non-zero? Will phi have any influence if the Peclet number is very large negative value? Excuse me. What is your expectation? Phi Peclet number very large negative means from which direction flow is coming? From the west or east?
Sir, from the east.
East.
From the east. So east side value phi e should have a major influence, right? Is it clear?
Yes, sir.
Yes, sir.
In that case, AE should be, AE cannot be 0, right? AE should be some, AE should have some value. It cannot be 0, right? It should have some major influence. If A is 0, then phi influence will not be there. So A should have some influence and AW will be 0. Okay. So let us see actually what is the case. What is A by D in this case? This part looks slightly tricky, but once you go through them again, you will see that this is not difficult to understand. If Peclet number tends to minus infinity, A by D is equal to limit of Peclet number tends to minus infinity, P by e to the power P minus 1, this same expression. E to the power P, if P tends to negative infinity, e to the power P tends to 0. Okay. E to the power minus something, e to the power something negative. Okay, so if the value is very large, it will tend to 0. So we are left with P by minus 1. So it is minus PE. Okay. So A by D is equal to minus P. P is negative, so minus P is positive. Okay. So at the limit that Peclet number tends to infinity, minus infinity, the coefficient tends to minus Peclet number. So the coefficient has a higher and higher value for larger and larger negative Peclet number because the effect should be more and more dominant. at larger and larger flow rate. Okay, and that is what we are seeing. Okay, so if I draw these two lines, one is A by D is equal to 0 for positive Peclet number. This line looks like this. Okay, this dark blue line from P equal to 0. Say this is the P equal to 0 point. I hope you can see this. Okay, this is the P equal to 0 point. The dark blue line on the right hand side is A by D is equal to 0. Okay, and the dark blue line on the left hand side is A by D is equal to minus P. Okay, it's a linear variation. A by D is equal to minus P. So at P equal to 0, this is 0, and then it linearly increases in the negative direction. Okay, the y axis is A by D and the x axis is P. Okay, and the center point where you see the vertical red line is P equal to 0. On left side we have negative Peclet number, on the right hand side we have positive Peclet number. And this graph actually we are drawing to see what is the variation of A by D with Peclet number. Okay, we have found the two limits. One limit is A by D equal to 0 at very far infinity on the right hand side, and other limit is A by D is equal to minus P on the very far infinity on the left hand side. In between we don't know what is the exact variation. Okay, that is what we are trying to find. So we are assuming that the variation of A by D looks something like that given by this light blue or cyan colored line. Okay, light blue line. So it matches with the asymptotic value on the left hand negative, means left hand side, left infinity, negative infinity, and also it matches with asymptotically with the positive infinity value, and in between it varies smoothly between these two values. Okay, so we will try to find also the value at Peclet number equal to 0. Okay, because this is another important case where there is no flow at all. Okay, so what is the value at that point? So at Peclet number equal to 0, A by D is equal to limit Peclet number equal tends to 0, P by e to the power P minus 1. Okay, this is e to the power x minus 1 by x. Limit of that if x tends to 0 is 1. We have already discussed. So this limit is equal to 1. Okay, so A by D is equal to 1 at Peclet number equal to 0. So this light blue line crosses this vertical red line at a value of 1. So A by D is 1 when Peclet number is equal to 0. Okay, so we have 3 points. We have the minus negative point plus negative minus infinity point plus infinity point and 0 point. Okay, and the line goes through this. Okay, this is the behavior of the value A by D. Okay, so if we analyze this physically, it means that for larger and larger positive values, the influence of A by D becomes smaller and smaller. The value of A by D becomes smaller and smaller. Ultimately, it goes to 0. So for larger Peclet number, larger positive flows, the value of phi is actually becomes lesser and lesser. The effect of phi. On the other hand, for larger and larger negative values, the A by D increases, keeps on increasing. So we have more and more effect of phi E for larger and larger negative values as we expect, because the flow is coming from the direction of east for large negative values. Okay, so we assume that phi E should have a very strong influence. Okay, that is what we are seeing here. Any questions? Okay. So this variation, okay, A by D, this is the exponential variation, the thin, the light blue line, cyan colored line. But now we are going to break this into 3 different parts. Okay, and each of them has a straight line. And by using this part by part representation, we will find the value of A by D. Okay, the coefficient A. Ultimately, we are trying to find the coefficient values AE and AW. So this method, where we divide this behavior part by part into linear variations, is known as hybrid scheme. Okay, so in hybrid scheme, this is represented by combining 3 straight lines. Okay, what are these 3 straight lines? I will keep this diagram open here. What are the three straight lines? One straight line is y is equal to 0 if x is much greater than 0. Okay. So this dark blue line, okay, y is equal to 0, y equal to 0 line, and this is valid if x is much greater than 0. Okay. Second is y is equal to minus x if x is much less than 0. So this line, okay. So if x is much less than 0, y is equal to minus x. This dark blue line on the left hand side. And third line is, we will draw a third straight line in between these two lines such that is tangent. Okay, so this is this straight line. Third line is tangent to the actual curve at Peclet number equal to 0. Okay, so that we get some more characteristics correctly involved in our hybrid scheme. Okay, so the third line is a straight line in between these two lines which we have already denoted, for which, okay, which is tangent basically. This third line is a tangent to the exponential curve at x equal to 0, at Peclet number equal to 0. This third line is a tangent. Okay, so let us see how it looks like. Okay, so here y denotes a by d and x denotes Peclet number. Okay, y denotes a by d and x denotes Peclet number. So one line is this line. I hope you can see this. Second line is this line, the right hand side, and the third line is in between these two lines. Okay, this blue line, the slanted blue line, going from the negative side to the positive Peclet number side, and is tangent to the red curve, which is the exact solution. Okay, it is tangent to the red curve. Okay, now we do not know from which extent we should start this line and from where we will end this line. We have to find these two intersection points. Okay, but this is the idea, that at a certain range in between, starting from some negative value to certain positive value, we will be using this tangent as a representation of a by d. For further positive values, we will be using y equal to 0, means a by d equal to 0. And for further negative values on the left hand side, we will be using y is equal to minus x, or a by d is equal to minus Peclet number. Okay, but in between we will be using the value of the tangent. Okay, so that we can accurately capture the low Peclet number effect also. Okay, this is the idea behind the hybrid scheme. So we need to find out these intersection points, which I have shown here by this vertical light blue lines. Okay, the vertical light blue lines are the showing at what Peclet number the intersection occurs between these lines. Okay, so to find the intersection of the curves, we can find the slope of the middle line. We have to find the slope of the middle line. Slope of the middle line is the slope of the tangent of the exact solution at Peclet number equal to 0. Okay, so as it is tangent to the exponential curve at x equal to 0, tangent at x equal to 0 we have to find. Okay, so the expression for tangent at x equal to 0 is, so at this point the value of y is 1 and x is 0. Okay, so y minus 1 is equal to dy dx at x equal to 0 into x minus 0. This is basically equation of a line going to the point 0 1. Okay, y minus 1 is equal to dy dx at x equal to 0, x minus 0, equation of a line going to the point 0 1. Okay, basic class 12 maths. So now dy dx we have to find. Okay, so what is dy dx? What is y? If I write y is basically x by e to the power x minus 1. Remember, x is Peclet number and y is this term. Okay, a by d. Okay, so y is this term, a by d, and x is Peclet number. So y is equal to x by e to the power x minus 1. Okay, so dy dx you have to differentiate with respect to x. So you will get one term, you will get by differentiating the numerator. So you will get 1 by e to the power x minus 1. So this is the term 1 by e to the power x minus 1. Second term you will get by differentiating the denominator. So you will have already have x, then minus of 1 by e to the power x minus 1 whole square. Okay, so x into minus of e to the power x minus 1 whole square, then differentiation of e to the power x minus 1, which is e to the power x. Okay. So if you do it, you will see that this is the second term for the differentiation. So ultimately dy dx for this term is minus x e to the power x divided by e to the power x minus 1 whole square plus 1 by e to the power x minus 1. Okay. At x tends to 0, dy dx is equal to limit x tends to 0. So you just take both these terms together, e to the power x minus 1 whole square. So we have x e to the power minus x e to the power x, this term, plus e to the power x minus 1 for this term. Okay, plus e to the power x minus 1. Using L'Hopital's rule now, again we have to differentiate the numerator and the denominator. Okay. So dy dx at x tends to 0 is equal to limit at x tends to 0. Differentiation of the numerator is minus e to the power x minus x e to the power x for the first term. For the second term, it is e to the power x. Okay, third term is 0. For the denominator, it is 2 e to the power x minus 1 into e to the power x. Okay. For x, so now you can cancel e to the power x from the numerator and denominator. So you are left with minus x divided by 2 e to the power x minus 1. Okay. So at limit x tends to 0, x by e to the power x minus 1 is 1, right? So we are left with minus half into 1, so it is minus half. So this limit of dy dx at x tends to 0 is minus half. Okay, slope of the tangent is minus half at this point. Okay, so now we can write the equation of the tangent as y minus 1 is equal to minus half x minus 0. Okay, y minus 1 is equal to minus half x minus 0, so it is equal to x. Okay, so my y minus 1 is equal to minus half x, or y is equal to 1 plus half x. This is the equation for this middle line. What are the three equations now? One equation is y is equal to 0. Second equation is y is equal to minus x. Third equation is y is equal to 1 plus 1 minus half x. Okay, third equation is y 1 minus half x. To find the intersection on the left hand side, we have to find the common value for these two lines, y is equal to minus x and y is equal to 1 minus half x, because both the lines will have the same value at this intersection. Okay, so y is equal to minus x is this line. I hope you can see this. And y is equal to 1 minus half x is this line. Okay. So one is this line. Let me use some other color. So one is this line, okay, and another is this line. So this is the intersection point. So this line has a slope, this line has an equation y is equal to minus x, and this line has an equation y is equal to 1 minus half x. So at the intersection, both the lines should have the same value of y and x. So we can find that common value, y is equal to minus x and y is equal to 1 minus half x. So if I replace minus x in this expression, we get minus x is equal to 1 minus half x, or x equal to minus 2. So at x equal to minus 2, so this point is x equal to minus 2. It's difficult to write using a mouse. So this is x equal to minus 2. Okay, Peclet number equal to minus 2, this point. At this point, both the lines intersect. Okay, so this is our left hand intersection. For the right hand intersection, y is equal to 0 is one line. This line is y is equal to 0. And this line is still the same line, y is equal to 1 minus half x. So if you put this, you get 1 minus half is equal to minus 1 is equal to minus half x, or x equal to 2. So this other point is x equal to 2. Okay. So now we can write the hybrid scheme in full. Okay. For x less than minus 2, So for x less than -2 up to minus infinity. So any value less than -2 towards the minus infinity direction, we will write y is equal to minus x, or a by d is equal to minus Peclet number. For x equal to -2 to x equal to 2, we will write a by d is equal to 1 minus p by 2, or this equation basically, a by d is equal to 1 minus p by 2. And for x equal to 2 to any value greater than 2, means up to positive infinity, we will write a by d is equal to 0, means y is equal to 0. Okay. So these are the three lines. So finally, the hybrid scheme can be written as a by d is equal to minus p if Peclet number is less than -2, 1 minus p by 2 if Peclet number is between -2 and +2, and 0 if Peclet number is greater than 2. Okay. So by using these three lines, okay, we are mimicking the behavior of the exact solution, exponential solution, but without using any computationally intensive calculation. Okay, just simple calculations we are using to mimic the behavior. Similarly, AW by DW also can be found. We will not go into the details, okay, which is beyond the scope of this course, but in a similar manner that can be also obtained. Okay, and this scheme is known as the hybrid scheme. So once you find the AE by DE and AW by DW using this method, by fitting these lines, you can then find AP is equal to AE plus AW and use those value of AE, AW and AP for solving, for discretizing the equations, and you will get very accurate solution, somewhat similar to exponential solution, but at a very faster rate, means calculation will be much faster. This can be written in a compact form also in this manner by using the max function, maximum function. We can write this, couple all these three together in a single equation as A by D is equal to maximum of minus P, 1 minus P by 2 and 0. Okay, you will see that this satisfies these individual equations for the correct ranges. For example, if Peclet number is less than -2, okay, Peclet number is less than -2, first equation should be satisfied. So if Peclet number is less than -2, this minus Peclet number is greater than 2. Okay, then 1 minus Peclet number by 2. Okay, so this term will be lesser than this minus Peclet number. Okay, and other term is 0, obviously is the least value. So minus p should be the greatest term if Peclet number is less than -2. Similarly, if Peclet number is greater than 2, minus p is obviously less than 0. 1 minus p by 2 is also less than 0. So 0 is the largest term. So if p is greater than 2, 0 is the largest term. And in between, say if Peclet number is 0 or 1 or anything in between -2 and 2, say if Peclet number is 1. Okay. So this is -1. This is 1 minus 1 by 2. Okay. So this is -1. This is half. And this is 0. Okay. So -1, half and 0, the largest number is half. Okay. So 1 minus p by 2. You can see for other cases also that any value, if Peclet number is between -2 and 2, this middle term will be the highest, will have the highest value. Okay. So in a compact form, we can write this in this form. Okay. So I will just, for the sake of completeness, I will write the entire scheme, but we will not derive it, and I am also not expecting you to derive it in the exam or anywhere. But the full hybrid scheme can be written as AP phi p is equal to AE phi plus AW phi W, where AE is equal to maximum of, see, if AE by DE is this, so if AE will be equal to this into DE. Okay, so Peclet number into D is FE. Okay, Peclet number is defined as FE by DE, right? So AE is equal to maximum of minus FE, D minus FE by 2 and 0. Same equation, this one only. Just D has been taken to the other side. Okay, so A is equal to maximum of minus FE, D minus FE by 2 and 0. AW also can be derived as maximum of FW, DW plus FW by 2 and 0. And AP is equal to AE plus AW plus FE minus FW. Fp minus Fw will be 0 due to continuity equation. Okay, so Fp is equal to A plus Fw. This is the full hybrid scheme. In case you want to use it for any code or anything, you can use this scheme. You don't need to derive it or don't need to know how to derive the AW. But whatever we have discussed, you should understand up to this point. Couple of points to note. This scheme is identical to the central difference scheme between Peclet number of -2 and 2. Okay, so for low Peclet number, this part, okay, this variation is same as the central difference scheme. If you go back to central difference scheme, you will see that the variation is same. Okay, we assume that this is the variation. Okay, linear variation, and assuming that diffusion is the dominant function. Okay, so this scheme is also identical to central difference scheme, and it is identical to the upwind scheme for x greater than 2 and x less than -2. Okay, but with the diffusion term equal to 0. In the upwind scheme, we had the diffusion terms. Here we will assume that the diffusion terms are equal to 0. So with diffusion terms equal to 0 means there is no diffusion at all. It is only flow dominant. Otherwise, this is exactly same as upwind scheme. Okay, like for these two parts. Any question?
No, sir.
Please go through this material. Okay, this is important because these are the schemes that are used practically. The central difference upwind also is used in many cases. Even we use upwind scheme because it is very simple to implement, and with fine grids, upwind also gives very good results. But with a coarser grid, these are the more accurate schemes. Okay, but you will find upwind even in commercial packages. Lot of schemes use upwinds. Lot of methods use upwind scheme. Anyway, so we will finish this part by briefly introducing another scheme which is actually a very accurate scheme. It is known as power law scheme. It is also used very widely, and we will not go into the derivation of this scheme. Okay, we will not go into the derivation of this scheme. I will just state what is this scheme, and because it's a very important scheme, and then we will conclude this part about convection diffusion problem. Okay, and then we will go into the final topic, which is a short topic on how to solve the Navier-Stokes equation. Okay. So this scheme is known as power law scheme. This is the final scheme that we are going to study, and I will just state what is this scheme and what is the idea behind this scheme. Okay, idea is again similar. So last time let me go back to the original. Okay, this was the scheme, right? So we had equated this exact curve, the red line, by using three straight lines. Okay, instead of using these three straight lines, what we are going to do is we will be using four lines. Okay, to mimic this. Okay, we will be using four lines to mimic this. What you can see here for the hybrid scheme is that there is a considerable difference. Okay, with the exact solution at the value where the intersection occurs. Like for example, at Peclet number +2 and -2, we see that there is quite a bit of difference between the exact solution and the hybrid solution. Other places the gap is small, but at this location the gap is quite high. Okay, there is still some differences. So it is not as accurate. Okay, we can see graphically itself that there is a quite a bit of difference. Okay, this amount of difference is there at these points. So if we can mimic this rate curve in a better way, then we should target to do that. Okay. So this next scheme, power law scheme, what it does it divides this rate curve into 4 curves. Okay. One is starting from Peclet number greater than 10. Okay. So at Peclet number equal to 2, still the value is quite large as compared to 0. But once you go to Peclet number 10, this value is almost equal to 0. Okay, at very large Peclet number. Similarly, once you go to Peclet number minus 10, this value is almost equal to minus p. There is not at all much difference. Okay. So for Peclet number minus 10, okay, something like this minus 10 and Peclet number plus 10, beyond these two ranges, we will be using what we have already derived, two straight lines. Okay, what the straight lines that we have already derived, we will be using those straight lines. A by d is equal to minus p for Peclet number less than minus 10 up to minus infinity. Okay, and A by d is equal to 0 for Peclet number greater than 10. Okay, up to plus infinity. But in between these two, we will try to fit a better curve. Okay, we will try to fit a better curve so that it mimics the red line in a better way. My drawing is not very accurate, but it will give you the idea. Okay, we are not trying to follow the straight line, we are trying to follow the red line. Okay, from here to here, and even in this section, we are trying to follow the red line, but without using exponential. Okay, so it has been seen by trying different formula and trying to find out the least error. Okay, minimum error, least square error. It has been found that 1 plus 0.1 p to the power 5 minus p. Okay, a very arbitrary value, but it has been obtained after trial and error. It is seen that this curve 1 plus 0.1 p to the power 5 minus p, this actually mimics the red line, the exponential curve, in a very good way between the value of minus 10 and 0. Similarly, the curve 1 minus 0.1 p whole to the power 5, this mimics the exponential value between 0 and 10 in a very good way. Means almost you will not be able to check the difference through naked eye if you plot the two curves, the exponential curve and this power curve. Okay, this is power curve, right? This is based on power, fifth power. So if I plot this power curve as variation with Peclet number, y is equal to 1 minus 0.1 p to the power 5, and I plot the actual exponential, we will not be able to even see the difference between the two lines. It will look visually similar. Only when we plot, when we actually calculate the difference, we'll see that there are differences 10 to the power minus 5, minus 6 of that order. Okay, so this is actually very good replication of the exponential solution. Okay, these two curves. Okay, in between minus 10 and 0 and 0 and 10. So this entire set of values, these 4 lines, okay, these are not straight lines. We have 2 straight lines and 2 curves, power curves. Okay, this entire set of values together comprise what we call as power law. Okay, power law scheme. This is the power law scheme. So we can also write this as, again we can combine this in a single line. I leave it to you to understand how it is, like whether this satisfies all the conditions. You will see that it satisfies all the conditions. So A by D is equal to maximum of 0, comma 1 minus 0.1 mod of Fe by D whole to the power 5, maximum of 0, comma minus Fe by D. You will see that for any values within this range, minus infinity and plus infinity, it will satisfy the correct option out of these 4 options. This will satisfy the correct option. So whatever is the correct value automatically. So actually we are writing all the 4 equations in a single equation. You can write like this also, or you can write them together in this manner. Why the second type of equation is suitable? Because in that case it is easier to write in a computer program using the max function, but if in the first case is also fine using if loops. Okay. Similarly, AW by DW can also be defined. Okay. So this scheme, which is known as the power law scheme, is very, very accurate. Okay, and very closely follows the exponential scheme. But you do not have to calculate any exponential. you only have to calculate a set of powers, but only single set of power. Okay. For exponential series, for each term you have to calculate powers. Here only single set of powers. Okay. So it's much more efficient as compared to exponential series, but almost gives the same result as the exponential series. So with this, actually we will finish this part, the convection diffusion part. We have studied about 5 schemes. Okay, the central difference scheme, which is the most basic or intuitive scheme, the upwind scheme, which is also very basic but is quite useful in case you have a very high flow rate. Okay, it's very useful. Central difference scheme is useful when you have very low flow rate or negligible flow rate. Okay. Then the third scheme is the exponential scheme, which is the exact scheme, which gives us the exact solution for a simple problem. For a complicated problem also it gives very accurate solution, but it is very computationally intensive. And then we have seen 2 types of piece by piece schemes. One is the hybrid scheme, which actually is an amalgamation of 3 straight lines. So you combine 3 straight lines to mimic the exponential behavior, and it gives quite accurate solution. Only place it gives slightly inaccurate solution is Peclet number -2 and Peclet number +2. Otherwise, it is quite accurate. At very large Peclet number, this becomes equal to the upwind scheme, and at very low Peclet number, this becomes equal to the central difference scheme. And finally, we have just briefly mentioned something called power loss scheme, where you can exactly mimic, almost exactly mimic the behavior of the exponential curve. So the solution is almost as accurate as the exponential solution, but without the complicated calculation. Okay, calculation is very simple. So the task, if say somebody is writing a code, okay, the task of discretization is as well means you have the set of convective diffusive equations with source term and unsteady term. So we already know how to discretize the unsteady and source term. For the convective diffusive term, we have to select any one of these schemes. For example, somebody may select the exponential scheme, or somebody may select the power law scheme. Okay. Then we know what should be the variation of AE by D. Okay. And we will find out what should be the value of AE. Say if I select hybrid scheme. Okay. So we know that AE should be like this and AW should be given by this. AE should be max of minus FE, DE minus FE by 2, comma 0, and AW should be max of FW, comma DW plus FW by 2, comma 0. Okay. So once you know what is AW and FW equations, at each point you can calculate what is the, sorry, AE and AW at each point you can calculate the value of AE and AW and then the value of AP. Okay. And based on those, then you will be supplying those values to the solver, and we can use TDMA or any other solution mechanism where the input of the coefficient values, as we have already seen previously. Once you know the coefficients, using the coefficients you can solve for the variable. You will find the set of variables for the entire domain. So what does this part do? This part actually gives us the value of the coefficients AE, AW and AP for each grid point and supplies it to the solver part, where these coefficient values are taken as an input for finding the values of the phi at each grid point. Okay, this is how solution is done in 2 steps. Previously also it was done in the same way. Only thing that has changed is what is the value of AE, AW, things like that. Previously they only had diffusive terms. Now we have both diffusive as well as flow terms also, as you can see here. Both diffusion term is there as well as flow term also is there in the coefficients. In some cases flow term will vanish, in some cases diffusion term will vanish, but in general both of the terms are there for a general convection diffusion problem. Okay. Any questions? This part is very well defined or well described in the book by Patankar. Okay, but in a brief manner only, like what I have discussed. Okay, Patankar book is more like a notes. Patankar himself was the pioneer in developing lot of these schemes. The schemes that we are going to study next for solving convection diffusion problem means Navier-Stokes equation. The simple and simpler, those were actually derived by Patankar himself, means invented by Patankar. So He is a pioneer in this area. His book is also, that's why, very famous. So you can go through the book, and it has this type of description only, but some small nuances are there, and it can give you some insight if you think deeply about each of the points that are described. Without much discussion, he has just written the points, but that actually gives us a lot of insight if you think about each case. So CFD is like this. You have to think about all this situation. If you just go through in a ritualistic manner, then you will not. It is, as I always explain, like it is like trying to learn swimming by seeing swimming tutorial or YouTube videos. Unless you actually start swimming, or unless you actually start solving CFD problems, you cannot learn CFD. Okay, you can know the technique and everything as good as possible, but until you actually start doing it, you will not know what are the tricks and tricks which has to be used. I will take a break. I am feeling that I can continue today. Okay, so I will take a break and continue this to the next part, so that at least the CFD part we are almost like we don't have to take any extra classes or anything. And then we will discuss what is to be done with the power plant engineering course. Any questions? No questions, huh? So let us take a break. Yes, something you want to ask?
Sir, I wanted to ask regarding that this course project, sir.
Yes, tell me.
Sir, the example you gave is are we supposed to consider PCM there, or we can take any
No,
CFD
no, no.
based?
That is just an example that I have given. Assuming that I am solving a PCM problem, you can take any CFD problem. Okay, okay. I think there is some confusion here. Need not be, means my point of giving that example was that how you should
Present the first
present the problem. Okay.
Yes.
Say for example, I want to solve a flow in a room due to presence of air conditioner. Okay. I'm just giving some other example. So there is flow in a room and the AC is running, or some simple conduction problem. Okay, I have a plate. Okay, I have a 2D plate. Okay, rectangular plate, and in between I have put a heater at the center of the plate. Okay, and the heater is giving certain amount of heat flux, 100 watt per centimeter square or something like that. Okay, so then I want to solve that problem. Okay, so what will be the variation of temperature for that plate with time if certain boundary conditions are there? So for example, the plate has a length of 1 meter by 1 meter and all the boundaries are at 300 Kelvin temperature. Initial temperature of the plate is also 300 Kelvin, and I have put a heat source at the center. So how the temperature evolves with time, this is a one CFD problem I can solve. Okay, by writing a simple 2D code, diffusion means diffusion based code, whatever we have studied previously using finite uh, finite difference scheme. I can easily solve this. Okay, you will be able to easily solve this problem in 2D or in 1D, some 1D problem. Say you have a processor. Okay, it is releasing certain amount of heat. Okay, processor which is releasing 45 watt of heat. Okay, and I am assuming that there is a fin connected to it. Okay, one single fin connected to it, as if like a 1D problem. So at one end of the feed we have a 45 watt heat, on the other side it is removing heat to the atmosphere. Okay, so whether we can solve it using simple coding. Okay, this is also one problem that can be tackled. Somebody can think that no, I will use ANSYS. I want to use ANSYS to solve a problem. So then the flow in the room. Okay, there is a room and one window is open and flow is coming from outside. Okay, so what is the flow pattern in the room? Or there is a AC switched on in the room, which is bringing cold air and is removing hot air. Okay, so what is the flow pattern in the room? They can develop a simple cubic geometry in ANSYS and then give some inlet condition in a rectangular position on the wall in to represent the AC, and some outflow condition also nearby by the AC is bringing out the hot air. and see what is the flow pattern in the room, okay, for different AC velocities or temperatures. Similarly, somebody can try to solve some other law. It was just an example to show how to represent a problem. Like what are the important parameters? Problem description, boundary conditions, domain. Okay, so that you can, so whatever is your problem. So if it's a 2D conduction problem, what will be your domain? It's a square domain. What are the boundary conditions? What are the initial conditions? Okay, there is a heater in the center. What is the initial temperature? What is the boundary temperature? Whether it is insulated or not. Then what you are trying to achieve? What is the objective of your problem? This you need to outline so that you know that your problem is clearly defined. That this is my problem and this is what I am trying to find out of this problem. Is it clear? It can be on any area of CFD. Last time students have done very, I don't have their presentations, but actually they had done, they had lot of time last time because of lockdown. And I did not ask them to present just after finishing the course. I asked them to present after the end-sem exam. So in between they got 2 months or something like that. End-sem was delayed last time. So they actually did, all of them did very good projects. Some of them did on, like I was saying, liquid cooling of processors or graphics card, liquid cooling. Some students had done, so one group, and one other group had done something on like cooling of data centers, all practical type of, some had done more mathematical, like by writing their own code, solving a simple 2D heat conduction problem by writing their own code and seeing the accuracy for different schemes like this. Another student had used ANSYS actually to study something, I think flow in a microchannel, something like that. Okay, flow in a microchannel, droplet generation in a microchannel, something like that. And then there were cases where people have studied uh, radiation type of problem, radiation based problems. Then one interesting project was there on ion propulsion, like one team had done on ion propulsion. So CFD analysis of say hypothetical spacecrafts using ion propulsion, and they had done some analytically, almost semi-analytical, like using equations, and by solving them semi-analytically they found out at like what will be the propulsive force that is generated for the spacecraft to move ahead. A lot of interesting projects were there. Need not be very, if you sit down for few days you will be able to do those kind of projects. The main trick is to understand how to simplify a complex problem into a very simple problem which is solvable. Okay, you should not take one problem which is not possible to solve at all in this limited time. For you guys the time is limited, right? I would like to see the presentation just after the exams are over, because I have to submit the grades after that. So you have some time now, and then not much time is left. So within the limited time, so that's why the scope of, you don't try to tackle a very extravagant problem. Try to say, just do a very simple problem, which shows that you know how to do CFD. Okay, okay, that is more important. It is not that marks are based on as complicated the problem, more will be the marks. It is just to see how clear is your understanding. Okay, I can take a 1D simple 1D problem, 1D conduction problem. I can write a simple code, and that itself will be a very good CFD assignment. If I can show how, say I have a rod or like a wire. One side is heated, one side is kept at cold temperature. How the temperature varies in that wire with time. If I can show, and I can show that it matches with the analytical solution, my CFD solution, it will be a very good problem. That is the idea. Okay. You can use ANSYS also for simple geometries. You can try to do some simple flow, like say there is an obstruction. There is a channel and there is an obstruction. Okay, blob body it is called. So for example, say circular body is there, or a square body is there, 2D domain is there, and flow is coming from the left hand side and passing over the body. So what is the pattern of the flow? Okay, what is the lift and drag coefficient, or what is the pattern of the flow? If you can show that, those type of simulation. Okay, so that is also interesting very. So flow around a corner, there is a corner, or natural convection. So many things are there. Hundreds of things are there in CFD. All of them can be quite interesting. So you can target any of this and you can try to do. But take a simple problem, okay, very simple problem, which is feasible to be done within the limited time. Think of it as an assignment problem, okay, a longish assignment problem. If you have time, you can do even better, but you have to dedicate then some more time, okay. So, because once you start, you will see that there are a lot of bottlenecks, okay. Is it clear, or any questions regarding the project?
Clear.
Okay. So I will take a break, okay. I am feeling that I can continue. So I will take a break and we will continue. So I am back. Can you hear me?
Yes, sir.
Okay. Any other questions regarding the project or anything else? Time is very tight. Okay, so accordingly you adjust your quantity of work that can be done in the project. I am also not expecting that it is going to be a long project, something like that. Just to show that you understand principles of CFD. Okay. Presentation will be there at the end. So let us go to the final topic, which is calculation of flow field. Okay. The screen is still visible, right? Calculation of flow field.
Yes, sir.
Yes, sir.
Okay. So before going into the details of how to calculate the flow field, so what we are going to do in this part is we are going to see or derive, not exactly derive, we will basically we will engineer or we will discuss two schemes for solving the Navier-Stokes equations. One is known as simple and the second one is known as simpler. Okay, very popular schemes. And before doing that, so those schemes can be used for solving Navier-Stokes equation, but why these special schemes are required, that we will try to understand a little bit. Why it is not, why we have to treat this flow field calculation as a separate topic, why it is not part of the normal convection diffusion problem. That is what we will try to understand a little bit before we try to go through the algorithms. But the algorithms, simple and simpler, are very famous, and you will see in many papers, or even if in our papers also you will see that we cite that we have solved the Navier-Stokes equation using simpler algorithm, something like that is written, which because these are quite popular. Even in your software also you will have the option of using simpler or something like Simplec or PISO. All these are different types of algorithms for solving Navier-Stokes equation, and simpler is one of the best ones. Okay. So before that, let us try to understand some of the difficulties which are there for solving the flow field. Okay. So solution of flow field is, I have already written them here in like everything is already written here. So you can go through this part also and try to understand, but let me explain. Solution of flow field is more difficult as compared to other convective diffusive equations. Okay. What are the difficulties? The difficulties are that one is that there is a pressure turn in the in the Navier-Stokes equation. Any other convection diffusion equation, like for example energy equation with convective turn, will not have any extra variables. Okay, unknown variables. But here in our case, in the Navier-Stokes equation, there is a pressure variable which is also unknown. Okay, and there is no equation for this pressure. There is no direct equation for pressure. For velocity, for energy equation, for example, there is an equation for temperature. For u velocity, there is an equation for u momentum. V momentum, there is an equation for v velocity. Similarly, w momentum, you have an equation for w velocity. However, there is no equation for pressure. Okay, that is a big problem. Second problem, momentum equation has terms which are non-linear. Okay, because there are terms like uv like this. Okay, you can see here rho uu. Okay, rho uv. These type of terms are present in momentum equation. Rho uu, rho vu, rho wu. So that makes it non-linear. Okay, and the third difficulty is that the momentum equations are coupled. Okay, so coupled means that you cannot independently solve the u equation. In the u equation, you have the v velocity term also, w velocity term also. So you have to solve them together. Okay, even for the pressure, there is no extra equation. So later we will see that for pressure we have to use the continuity equation. Okay, so we will have four equations: one continuity and three momentum equation, and four unknowns: u component of velocity, v component of velocity, w component of velocity, and pressure P. Okay, so all this has to be solved in a coupled manner because each of them depend on the other. Okay, you cannot independently solve them. Unlike the cases like what we have previously discussed. Okay, so that is the third difficulty. Okay, so in general, the continuity and momentum equations can be written like this: del rho del t plus del dot rho u equal to 0, and del t of rho u plus del dot rho u, where u is the vector u, is equal to del dot mu gradient of u minus gradient of p plus any body forces. Okay, b, vector b. So for example, for the x momentum equation, this is the combination of both x, y and z, all the three together in vector form. But if you want to separately write them, for x momentum, we can write them as del t of rho u plus del x of rho u plus del y of rho vu plus del z of rho wu is equal to mu del square u del x square plus mu del square u del y square plus mu del square u del z square minus del p del x plus bx, where bx is the body force along the x direction. For example, gravity will be the body force along the negative y direction. Okay, in general, in the way we take the coordinate systems. So similarly, you can write the y momentum and z momentum equation also. Okay, this is the general momentum equation, and you can see that there is the coupled terms plus the pressure term. So all these difficulties are present. Okay. And non-linearity. U type of term is there, non-linear. So now the issue of non-linearity and the coupled equations is not too difficult to tackle. Okay, non-linearity and coupled equation both are of similar nature. The difficulty are of similar nature and can be tackled using iterative method. How? For example, the UU term or UV term can be written as U star U or U star V. Okay, where U star is the previous iteration value of U. So while iterating, we already have at a certain iteration we have all the values, right? So we will be using these values for the next iteration. So part of the terms, so for example this u star u, so one u we will be taking from the previous iteration. Similarly here this u will be taking from previous iteration. So this will be known, so only one unknown will be there, one u or one v unknown will be there, and we can solve it like a normal convective diffusive problem, okay, with that unknown. But the result will not be correct because you are using guess value of u star and v star. So then with the new value of u and v, you have to again go through the same iteration and again find the new value of u and v. Like this you continue doing until you see that there is not much change in the value of u and v. Okay, then we say that convergence has been achieved. U and v are not changing much, and this is the final solution. Okay, so this is how we can tackle non-linearity as well as coupled equations by taking by using iterative method. Okay, it's not difficult. The main problem in solving the Navier-Stokes equation then comes from the first point that we have discussed, that there is no pressure, no equation for the pressure field. Okay, it's a big problem. However, solution of P is difficult as there is no direct equation for P. So, say for some reason or by some method, the pressure field is given to you. Somebody has measured the pressure field or has calculated using analytical solution or somehow has guessed the correct pressure and is given the pressure to you. Then there is no issue in solving the Navier-Stokes equation. Okay, we can just solve it in a similar manner to any other convective diffusive equation what we have discussed, like we can use the hybrid scheme or power law scheme or any of the schemes that we have discussed. Only thing is that the pressure term will be known because it is given to us, del P del X, and all the other terms will be the normal convective diffusive terms like this: unsteady term, normal convective terms, normal diffusive terms, and source term. And we can use hybrid scheme or exponential scheme or upwind scheme or any of these schemes to solve this problem. Okay. The only difficulty is coming because pressure field is not known to us and there is no equation for pressure. Also, if we can directly solve pressure somehow and fit that pressure in this equation, then there would be no issue. Okay. So that is the problem. So now we have one extra equation, the continuity equation, and somehow we have to find or cleverly manage some algorithm, cleverly find some algorithm so that the pressure can be obtained from the continuity equation. But the big issue is that in the continuity equation there is no pressure term. it only has density and velocity terms, del rho del t plus del dot rho u equal to 0. So in the continuity equation there is no pressure term, but we have to calculate the pressure from the continuity equation because we don't have any other option. So that is where lot of clever algorithms have been developed. How to convert this continuity equation into a equation from which we can calculate pressure. Okay, and that is what we are going to study in the next class or two. Okay. So there are some other any questions up to this point? Okay. I hope you guys are still there. Okay. At least visually you are there. You might be doing something else. Am I still audible?
Yes, sir.
Yes, sir.
Yes, sir.
Okay, okay. That's fine. Actually, I am taking this class with quite a bit of difficulty. So, but we have to finish the syllabus. We don't have any other option. So anyway, so what are the other difficulties in solving the flow field? Let us take a look at a couple of situations, okay, that may arise and which will be problematic. So let us go back to our very familiar discretization scheme. Okay, we have a control volume going from small w to small e. The control volume is represented by the grid point P at the center. Its neighboring grid points are capital E on the east side and capital W on the west side. Distance from the one face of the control volume to the other face is delta x. Okay, simple 1D discretization or grid generation. And for a 1D problem, we will have this dp dx term. Okay, 1D pressure, 1D momentum equation will have minus dp dx term. Okay, the pressure gradient term will be minus dp dx. Okay. So if we want to integrate this other terms, we know how to integrate. Other convective diffusive terms we know how to integrate over the control volume. So this new term minus dp dx, if we want to integrate over the control volume, how will we do it? Using finite volume method. We will integrate over the control volume. So going from small w to small e minus dp dx. Okay. This can be written as, because of negative sign, it comes as p at small w minus p at small e. Okay. Actually, integral of dp dx over the control volume is pe minus pw, but because of the negative sign, it comes as pw minus pe. Okay, this is the pressure gradient. So, but we don't have any pressure values at the interfaces, right? We always store all the values at the grid points. So, how will we calculate the pressure at the interface small w and small e? Or any values, how do we calculate at the interfaces small w and small e? How will we write Pw and Pe in terms of known values? Because P small w and P small e we do not know. At what locations do we know the pressure values? Means we don't know, but where we can store the pressure values? Or all variables are stored at what locations? At the grid points, right?
Yes.
So at capital P, capital W and capital E, we are storing all the values. So pressure values also will be stored at, means PW, P capital W will be there, P capital P will be there, P capital E will be there. So we have to interpolate based on this to find the interface values, right? So P small w we can write as P capital W plus PP by 2. Okay. Similarly, P small e we can write as PP plus PE by 2. Okay. Is this clear up to this point? Or any confusion is there?
Yes, sir. Clear.
Clear, right? So now writing this Pw minus P means integral of minus dp dx over the control volume. I will reduce the size, or what will we do? We will keep this open. Huh? So this diagram is required. Let us keep this diagram open. Integral of dp minus dp dx from small w to small e, we can write it as Pw minus P, which is P capital W plus PP by 2 minus PP minus PE by 2. Okay. So PP gets cancelled. We are left with P capital W minus PE by 2. Okay. So this value minus this, this value minus this value divided by 2. Okay. This is the integral value. So what is the problem with this then? Can we foresee some problem? So there are a couple of problems with this. Okay. One is that although our grid spacing is delta x, our pressure is being calculated on a grid spacing of 2 delta x. Okay. Because we are using, so for this grid point, we are calculating pressure as Pw plus minus Pe by 2. Similarly, for the next grid point, we will calculate it based on this grid point and whatever is the next grid point. Okay. So we are taking a pressure calculation is based on a coarser grid. This is a minor problem. It is a problem. Still, it is a problem because we want to have as refined grid as possible, and we are not taking the best option. But there is a major problem. Okay, what is this major problem? Let us consider a pressure field like this. Unphysical pressure field, which is not possible in real life. Okay. One point has 100, then it is 10, then 100, then 10, then 100, then 10. Okay, unphysical. So you cannot have this kind of wavy pressure field. Okay, because it will be quickly equated because of velocity. So in case the pressure field is like this, what should have happened in real life? Quickly the flow will go from pressure 100 to 10, and from this side also flow will go from pressure 100 to 10, and it will try to equalize the pressure. Similarly, from this 100 towards 10, pressure flow will go. From this 100 towards 10, flow will go. It will try to equalize the pressure. Okay. But in our discretized scheme, what are we getting? We get that dp dx is given by Pw minus P by 2, means alternate points. One of the points is omitted. So it will be given as 100 minus 100 by 2 for this grid point. Similarly, for the next grid point, it will be 10 minus 10 by 2. For the next grid point, it will be 100 minus 100 by 2. Okay. So in each case, we are finding that the pressure gradient is 0. Okay. Our discretized pressure gradients dp dx is 0 after this discretization. But which is truly means which is totally wrong, right? Because we see that there is a huge pressure gradient. There should be huge flow. But our discretization is giving that there is no pressure gradient anywhere. Any point you take, pressure gradient will be 0. If I take this point, pressure gradient is 0 because this 100 minus 100 by 2. If I take this point, pressure gradient is 0 because 10 minus 10 by 2. Okay. So because we are selecting alternate grid points, automatically because of this interpolation, it is causing a big problem. Unphysical pressure field is also being shown as a smooth pressure field, that there is no pressure variation. Okay, so in some cases, wavy and non-physical pressure field will also satisfy the discretized pressure gradient term, and no effect will be felt on the velocity. So if this type of pressure fluctuation occurs in say numerical calculation, we will find that there is no driving force on the velocity in our numerical solution, as if there is no pressure difference. So flow is, there will not be any flow because there is no pressure fluctuation. Numerical problem is feeling that there is no pressure fluctuation. In real life, there is a huge pressure fluctuation, but numerical problem is feeling that there is no pressure fluctuation, which is a big problem. Okay. Is this clear? What is the problem? With this discretization of pressure?
Yes.
Okay.
Yes, sir.
Similarly, let us consider another case. Okay, continuity equation, 1D problem. 1D problem without unsteady term. What is the continuity equation? Du dx equal to 0, right? For continuity equation for a 1D problem. And again, we have the same grid structure. So delta x is the length of the control volume going from small w to small e. It is represented by capital P at the center. Neighboring grid points are capital E and capital W. If you integrate the continuity equation over the control volume P, we get small w to small e du dx equal to 0, or u at E minus u at W equal to 0. Now there is no value at u at E and u at W. So again you have to interpolate u at small e is equal to u at capital E plus u at capital P by 2 Similarly, we had small w is equal to u at capital P plus u at capital W by 2. Okay, so you can replace this, and the UP will get cancelled. You will be left with UE minus UW equal to 0. Okay, the 2 actually goes away, so you are left with UE minus UW equal to 0. Okay, again the same problem will be there. Okay, the below wave flow field, which is, so I will show you one flow field. Okay, so say after some solution, or after this field is given to us 5, then velocity is 1, then velocity is 5, velocity is 1, velocity is 5, velocity is 1. This is clearly violating the continuity equation. Okay, because flow is not continuous. Flow velocity has to be same everywhere in a 1D problem. So it cannot be 5 at this point, then suddenly it will be 1, again 5, again 1. It cannot happen. This is clearly a unphysical situation. Okay, but what does our continuity equation say? UE minus UW equal to 0. Okay, so for this point 1, our continuity equation is being satisfied because it is 5 minus 5, 5 minus 5 by 5 minus 5, so 0. Similarly, for the next point, our continuity equation is satisfied, 1 minus 1 equal to 0. So any point you take as P, you will see that the continuity equation is satisfied. Although it is clear that this is a very wrong unphysical situation, our discretized continuity equation is satisfying this flow field. Okay, which is totally wrong. So it should not be the case. Okay, so same problem is again arising in this case also. And these problems are also present in 2D and 3D cases. Okay, this arises because of the interpolation that we are doing for calculating the velocity or pressure at the interfaces. Okay, that is causing our all these problems. So clearly we need some logic, something to be done to actually avoid this. Okay, so there is a mechanism which is known as formation of staggered grids, which can be used for the velocity to avoid this problem. So we will see what is this staggered grids. So grids are staggered. Staggered means they are moved by a certain distance with respect to the original grids. Okay, let us try to understand this, what it means. Okay, and how it is going to solve our problems. And it has a big role. Okay, so that's why it is actually quite important. Any questions up to this point? No questions. So let me see how much should we go today. We will go up to only 2 pages, and then we will continue in the next class. Okay, because we don't have much left. Still, it will take a couple of classes. We'll discuss. Anyway, so let us see. So what is this staggered grids? Okay, so there can be two types of arrangement of grids. Okay, velocity field, velocity grids. One is known as collocated grid, and second is known as staggered grids. Collocated grids is what we have discussed till now, means co-located. Okay, all the values are located at the same point. Okay, so for example, if I have a grid like this, WPE, my temperature, density, concentration, pressure, U velocity, V velocity, W velocity, all of them are located at the grid point. Similarly, at the next grid point again I have temperature, concentration, pressure, density, U velocity, V velocity, W velocity, everything. Okay, so each grid point stores all the information. Okay, this is collocated grids, co-located. Okay, located at the same point. In contrast, in staggered grids, what we have is the scalar values. Scalar values are like temperature, pressure, density. Okay, these are defined on the main grid points. Scalar values are defined on the main grid points. So P will still store density, temperature, pressure, concentration. Okay, all these values. However, the velocities, okay, velocity variable U, V, and W are not stored in the cell center. They are not stored in the grid points. They are stored at the faces. Okay. Their control volumes are itself shifted. I will come to this. And they are stored at the faces. The velocity variables u, v and w are defined on the points on the faces of the control volumes. Okay. That is, the grid points for the velocity are offset or staggered from the main grid point. Let us try to understand this through a picture. Okay. So that it is clear to you what I mean. What I mean by the offset. Okay. So let me explain this drawing. Okay. So this red lines are the original control volumes. Okay. Red line denotes the original control volume. Okay. So the central red line, what I am going to do is I am going to open this here so that I can draw also. Okay. So this, for example, the central control volume, okay, the central square is the control volume represented by the grid point P. Okay, so all the red boxes are, each of them is a control volume. So the central one is represented by the grid point P. Then this neighboring one is represented by the grid point T. On the other side, it is represented by grid point W. This below one is represented by south S, and the above one is represented by north N. Okay, if it is a 3D problem, you will have also top and bottom. Top will be outside the screen towards you, and bottom will be inside the screen away from you. Okay, out of the plane of the monitor or screen. So now these are the main control volumes and main grid points. Okay, and the temperature, pressure P, density rho, any other variable like concentration, Cp, conductivity, whatever is the variable. Okay, density, so already I mentioned. All these are stored in this point P, at this point E, at this point W, at this point S. Okay, except the velocities. For the velocities, the grid point itself is staggered, means the control volume. So for the u velocity, this is a control volume, the black line that you are seeing, over which I am drawing the green line. Okay, this black line that you are seeing is the control volume for the u velocity. Okay, so I have drawn the green line over the black line. So this is this control volume, you can see, is shifted by half control volume from the main red control volume or blue control volume. From the main P control volume, this green control volume is shifted by half towards the right hand side. Okay, and at its center is the velocity u. Okay, at its center is the velocity u. We will call it as u small e. Okay, or sometimes it is written as u half means I plus half comma j, something like this also is written, but we will call it as ue. Okay, u small e. So this is the velocity, and this is the control. This green line is the control volume for the velocity. Okay, so the grid point for the velocity is at the center of the this green control volume, and basically it is at the face of the original control volume. Okay, grid point for u is at the face of the original control volume, but at the center of this green control volume. Okay, so the grid point is staggered or offset by half distance, half control volume distance towards the right hand side. Okay, similarly this is another control volume. Okay, let us use the green color itself. Hello, can you hear me? Hello,
Yes.
Yes, sir.
my
Yes, yes, sir.
internet connection got cut, so uh, I got disconnected basically. So we'll continue. Okay. I think the screen needs to be shared again. Hello.
Yes, sir.
Yes, sir.
I am getting repeated calls and it's my net is getting disconnected because I am using my mobile internet from HOS and from director's office calls that come, so I have to take them also. Anyway, we will finish today. Where like I have lost track also. Yes, this was the case, right? Can you see my screen?
Yes, sir.
Yes,
Yes,
sir.
sir.
Okay, we will finish this part and in the next class we will continue. So I was showing that the other velocity means the next velocity, neighboring velocity UW will have its control volume also staggered. Means all the control volumes are staggered by half grid points or half control volumes in the x direction for the x velocities. Okay, they are not staggered in the y direction. You can see that they are still at the same height as p. Okay, they are at the same height as p. So they are not staggered in the y direction. Only in the x direction they are staggered. So next velocity where it will be defined? It will be defined here. Okay. Similarly, the previous velocity it will be defined here. Okay. Where other u velocities are defined? It is defined here. Then it is defined here. Okay. So these are all the u velocities. My mouse is. I am not very dexterous with my mouse, so you have to bear with this type of figure. So these are the all the u velocities. Okay. And they have their own control volume. You can imagine that each of them is at the central of their own control volume. For example, this will be the control volume for this u velocity. Okay, so this is for u velocity. Similarly, v velocities are staggered in the y direction. Okay, v velocities are staggered in the y direction. So the v velocity control volume will be like this. Okay. And this will be the v velocity. We will call it as Vn in this case. Similarly, the other v velocity control volume is this one. And this will be Vs. Okay. Similarly, the other v velocity is defined here, and other velocity is defined at this point. Okay. Similarly, we have v velocities at this point, at this point. So v velocities are not staggered in the x direction; they are only staggered in the y direction. As you can see, they are the same line as the p, but it is moved by in the y direction. Okay. Similarly, z will be moved in the third direction. Okay. So main grid is given by like this point,